Chris mentioned there's a little confusion on the shaft on the tanker. When you put something in a furnace, the outside initially, if you look at it in cross section this way, the outside's going to heat up, and that means it's going to want to expand. If you were to draw a little volume element here, it's going to want to expand, but it can't because of the stuff in the middle, which is still cold. So the outside goes into compression, and the center goes into tension. When you put a great big thing, put a roast beef in an oven, the outside starts to cook, it expands. The center is still cold, right? And so the two of them are tied together. So in that particular case, the crack that occurred in the shaft on the LNG tanker basically occurred when the metal was cold and the metal was still brittle. Steel goes through its ductile brittle transition temperature somewhere around room temperature. Hopefully we make steels better and we get the ductile brittle transition temperature below room temperature and below 0 degrees Fahrenheit and sometimes below 100 degrees Fahrenheit. But they hadn't done all the good heat treatment. They were still forging this thing to get it to shape, and then they were going to do the good heat treatment that gives you a finer grain size and gives you a lower ductile brittle transition temperature. So this material was still brittle, even at maybe plus 100 degrees Fahrenheit or even plus 200 degrees Fahrenheit in the center. If you put it in the furnace, in the center, or the outer fibers go into compression because it's expanding, the center has to go into tension to balance the forces, right? If you go back to mechanics, equilibrium of forces says if the thing is not moving off in some direction, all the internal forces have to balance to zero, sum to zero. Remember that somewhere? You know, sum of all the forces equals zero is one of the constraints for an internal structure. So the center was in tension when I first stuck it in the furnace. It was a brittle material. It had a defect, and we already talked about, or in the lectures, the videotapes, you saw the effect of a flaw on initiating a bigger flaw. And so they got what they call a clink defect, and they call it a clink because if you're in the forging shop, you can actually hear this thing. It's sort of like, they call it a clink, but it's more like a rifle shot going off. Okay, you can hear the crack pop in because it's a brittle fracture. And it only runs part way. They had a flaw here. It only ran until it ran out of tensile stress. When it ran into the compressive stress region, it stopped. And that's why it ends up as an internal ring of fracture. You've still got compression on the outer fibers, and so the crack stops. But it's there, and it covered about 2/3 of the diameter, because 2/3 of the diameter is roughly half the cross section, right? Yep.
Was that part not heat treated afterwards?
No, it was heat treated afterwards. But afterwards, well, what you have to do on really large parts is you have to put them into a furnace at an intermediate temperature and bring them up a little slower, and then put them in a furnace at a little bit higher temperature, or ramp the furnace temperature up. You don't just take something that's cold and throw it into a 700 degree furnace, because it kind of shocks it. It gets thermal shock. Okay. Now the problem with this is not really residual stresses. In those lectures also, I talk about residual stresses. In residual stresses, whatever the stress pattern is when you're at temperature, compression on the surface and tension in the center, when you cool things down, it'll be exactly the opposite, but I go through that on one of those tapes. Okay? Does anybody have any questions on why we get the clink in that thing? I apologize for Friday. I think it's the first time I've ever missed class in my career, but I was sat on the runway in McAllen, Texas for 6 hours because they had a bad thunderstorm in Houston. I got into Houston at midnight, which was kind of past my 7 o'clock departure for Boston, and I couldn't get back until Friday. But anyway, you've seen now 9 of those 12 videos. I'm around all of this week, first 2 days of next week, and hopefully by Columbus Day, we will actually have done 2/3 of this class. And you've now done 3/4 of the other class. So we're still on track to finish up a day or two before Halloween, both of the classes. And I won't be traveling as much in the next little while. Anybody have any questions on any of the other things besides from the other lectures that you had last week? I wanted to go back to friction welding and cold welding and stuff. We said that true area of contact is only a small fraction of the apparent area, remember, because the mountain peaks come together, but they have a certain indentation hardness strength. And even if you get to the point where the whole thing is starting to flow, just straight normal forces won't give you true 100% area of contact. You need interfacial sliding to get that, to break down those mountain peaks, to plow them away, and to get rid of the contamination. In friction and forge welding being one of the oldest types of welding, they were doing it thousands of years ago, basically extrudes the material out of the joint. You just push the contamination out of the joint. And ultrasonic welding, which is basically a micro motion, sliding motion, really doesn't get rid of the contamination. It just moves it around, and therefore you only get about 50% bonded area with ultrasonic welded joints. I once, for a paper, plotted the welding processes that have been invented over the last 125 years. Turns out the American Welding Society lists 199 different welding and cutting, or they call welding and allied processes, which includes cutting and stuff, thermal cutting and whatnot. And basically about 75% of those processes were developed between 1870, let's say, and 1950. And then between 1950 and 1975, there were probably another almost 25% of all the rest of the processes were developed. Since 1975, there's really only one new process that I know of, and it's called friction stir welding. I'll pass this around. Friction stir welding is a way to weld two plates together, typically aluminum, although there's a lot of research going on it right now, and people are trying to weld steel and titanium and other things. But basically, you just have a rotating pin that goes between the two joints. So the pin is rotating this way between the joint, and it just stirs up the metal. You don't melt the metal, you just heat it, and you're basically forging it, and you pull this little spinning pin along. This is one student gave me these. That's a friction stir weld from NASA, Michaud division down in let's see, is Michaud in Louisiana? I think it's Louisiana rather than Mississippi, but anyway, down where the Mississippi River exits into the Gulf, somewhere around there. Michaud builds the external tanks for the space shuttle. If you remember now, it's $20,000 a pound or $10,000 a pound, something like that, is the value of putting a pound of weight up into space. So they like to get weight out of that external tank of the space shuttle because it's a pretty heavy component. So they will spend lots of money to get thinner structures, better joints. One of the problems they have with that great big structure is distortion. And friction stir welding, because it doesn't melt the material and you don't have the big volume change between solid and liquid, friction stir welding will produce less distortion. So here's a picture passing around. They have a great big anvil. You can see a little joint right there. Here's the pin that's rotating at high speed and just carried along the joint. And essentially it's kind of forging the thing together. It is a new process. It was patented about like 1991 or 92 by the British. And Boeing has put in a $10 million friction stir welding line to help join some of their structural components for commercial aircraft and military aircraft. Most of the other friction stir welding machines have been research machines. People are still looking at it. It does produce less distortion because there's no melting, but does leave residual stresses in the joint. That's one of the things. It leaves weird microstructures in the joint, so the metallurgists are all excited. They can study all these weird microstructures. Anyway, it is probably the only new welding process in the last 25 years. So that's friction stir. We talked about linear friction where people are trying to put blades on disc. But I often use this time to talk about welding of steel rail. If you go and you go down to the subway down here and you look while you're waiting for the train to come by, you look carefully at the rail. About every 40 to 80 feet, somewhere in there, you will see a welded joint in the rail. It'll be kind of a little bulge along the side. Here's the steel rail, and it won't be on the top, but along the side you might see just kind of a little reinforcement bulge around there. There are three basic types, practical types of welding steel rail. Does anybody know why you want to weld steel rail? Right? It's less noisy. Okay, if you've ever been on a railroad track that was not welded, it goes clank, 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 and it's really noisy. But not only that, it wears much faster. If I have two things that come together, it's just a mechanical joint bolted together. The load as the heavy wheel goes off one and onto the other, causes severe wear, and that makes the noise even worse. If you go down to New Orleans, they have an old subway line, not a subway line, but a trolley car line, and it is terribly noisy. And if you get on it, you're going like this, okay? Because every time you go over a joint, they haven't replaced those. If you weld it, it's nice and smooth, and it's safer. You can't put high-speed trains like the Shinkansen, the bullet train in Japan, or the Acela here in the United States, unless you have all welded track. Okay, if you tried it with a high-speed train, as that thing starts to wear, one of the things that's going to come along, you're going to get a derailment. Now, you also get derailments for other reasons. What was the big train wreck this summer in Europe or India? I can't remember. I think there was one in both of them. But one of them was actually due to the fact they had welded rail, but in the heat of the sun, the welded rail actually buckled. I mean, let's face it. I mean, there's thermal expansion as the thing heats up in the sun. And they have to do something about that thermal expansion. It's not a problem in New England where the tracks curve, because you basically just design it so you have enough curves in the track such that when the thing heats up in the sun or cools down in the winter, the curve just expands or contracts sideways, okay, to change the thing. It's not a big amount, but if you're out in the middle of Nebraska, or Nebraska's not a good example, they got rolling hills. Let's take Kansas a little bit better, or the plains of Texas or something, where everything's flat and you just go straight. They actually have to put some expansion joints in the track, or sometimes they actually will zigzag purposely, although that gets a little expensive because it increases the length of the track. But they will zigzag things. Anybody been to a military base and seen what they do with the steam piping from the central place? They actually have the steam piping up above the ground, whereas in civilian places you bury it underground, so it's not unsightly. But on a military base, they actually elevate it about 3 or 4 feet above the ground. Why do they keep it above the ground on a military base? It's a holdover from the days of World War II and stuff. Your base gets bombed, and you lose your steam power by someone blowing a hole on your base, and to repair that, you got to go dig up the ground and everything else. If someone hits it with a bomb, whether it's in the ground or above the ground, it's easier to repair it if you actually put it above the ground to begin with. But the problem with that, if you go about 2 feet down here in Boston, the temperature of the soil is probably around 55 degrees, plus or minus 1 or 2 degrees. It just doesn't change temperature. That's what the old farmers used to do with root cellars, okay? They store the vegetables underground in a root cellar because it was cool and the temperature didn't change summer, winter, or fall. Now, if you go up to Alaska, they have permafrost, and the temperature doesn't change summer, winter, or fall, and it's below 32. In Fairbanks, Alaska, I think the permafrost is about 1,000 feet deep. Well, here in more temperate areas, basically you go down 1 or 2 feet, and you're below the frost line, and things won't freeze. So we can put pipe in the ground a couple feet deep, and it doesn't freeze, it doesn't change temperature, we don't have to worry about thermal expansion in general. But on a military base, when you put it above ground, what do? If you look at the base, you'll see as you go along, just for seeming no reason at all, they'll basically have about a 4-foot rise and a 5 or 6 foot wide piece and another one stepping down, right? And you see that they're ugly, they're all over. First couple times I grew up in Norfolk, Virginia area, Virginia Beach. The first time I saw these things on the base, I thought they were just going over a stream or something like that. Then I noticed they had them in the middle of nowhere. Of course, I was only in high school at the time, I didn't realize, but they're there for thermal expansion. Because it's not buried in the permafrost or in the ground where it's constant temperature. It's up above and it sees the temperature changes from, 10 degrees Fahrenheit in Norfolk, Virginia to 110 degrees Fahrenheit as the sun beats on it in the summer when it's 100 degrees out, okay? You gotta allow for thermal expansion. Well, it turns out one of these railroad trains this summer that killed a number of people, I can't remember where it was, but if I remember reading the papers correctly, it was basically, something happened, one of these expansion joints or whatever froze up, and in the heat of the sun during the summer, the thing expanded and the rail buckled. And so the train comes along, the rail's not straight like it's supposed to be, and it goes off, the wheels go off, and you have a problem. In any case, people like to weld rail because it makes it last a lot longer. You don't have to replace it as often. And the oldest technique is forge welding. A few years ago, I was asked by the Association of American Railroads to look into, better ways to weld rail. And so I went up here to Billerica, Massachusetts, and here it wasn't Amtrak back then, it was whoever it was, Boston Main Railroad or whatever, had a shop where they would weld the rail together. And they had nothing but a bunch of acetylene torches in a volume about this big, and they bring in one rail here, they had another rail here, and they heat the whole thing up for about 15 minutes. It takes about 15 minutes for the heat to soak through this big piece of steel. And then they had these big hydraulic rams, and they would just take this two ends of soft steel and just squeeze them together. And they'd extrude out 2 or 3 inches of flash. And then they have another hydraulic ram that will come along while this thing's still hot. They take the torches away, they come along and they shear that flash off. And then they'd let it cool down a little bit, and they'd have some guys grind it to finish it up. And they would end up, they had a train, a bunch of flat cars, and they would weld these things together in like 100 to 200 foot sections on this train. And the train, of course, you think the rail is kind of stiff and straight, right? Except if it's 100 feet long or 200 feet long, it's more like a piece of loose spaghetti. And a train will go off to wherever they're relaying the track, and they will put in the field, they'll put down 200 foot sections of track at a time. Okay, and just kind of pay it off, just slide it off the train bed and lay the new track. That's forge welding. Very slow process. It takes about a half an hour to make one joint. That's a pretty slow process, which is why they have a little shop, and they try to do that in the shop and take about a mile's worth of rail out there on this 200 or 300 foot long train, all stacked up, and lay it sometime probably in the middle of the night when none of the other trains are coming by. The next thing they do, I went over here to Brookline, Massachusetts to see flash welding. And what they were doing is on the green line, they were repairing some of the track. The problem is you can't shut down the green line for a bunch of hours, and you can't bring 100-foot long trains in with 100-foot long beams of stuff, so they actually have to do it in place, and they need a faster process. And so they were using flash welding, and they had this big yellow trailer, semi tractor trailer, that basically had big electrical generators. And they could pick up, they had some hydraulic things that would pick up the track. This was just kind of replacing the old track, so it would pick up the piece of steel track, the one that was on the ground. They'd take the bolts out of the railroad ties and lift it up, bring the two of them together, and then with these great big electrical generators, they would touch the two pieces of steel together, the ends of the rails, and they would then pull them apart while the currents, or while the voltage is on there, and they would strike an arc. It's a big arc. This is probably 5,000 or 10,000 amps in this arc. And they would slowly, they first pull it apart, and then they would slowly start pushing it back together, but they wouldn't close it so that, because if they did, they'd extinguish the arc, right? If you had a dead short. But they just let the arc play back and forth, and that very high current arc starts melting the ends of the steel. And it runs back and forth. Now sometimes we use magnetic fields to force the arc to run back and forth. We oscillate the magnetic fields to push the arc back and forth and get uniform, but you don't even have to do that. Wherever it starts getting closer together, the arc's going to want to go there, and if it's there, it's going to melt the stuff back. And so you get, it's like the 4th of July. It just sparks all over the place. You know, they had to cordon off a whole lane of traffic on either side of this thing while they're flashing this thing. It's very, very exciting, okay, to see this thing. And then after they flash it for about a minute or two, and they've eaten away about a ½ inch of steel on either side, the ram just squeezes the molten ends together. You get a little bit of flash, and you're actually making a fusion weld on the rail. That only takes 2 minutes, doesn't take 30 minutes to do that, and that's called flash welding. We do flash welding of sheets in steel mills. You want to run, you know, continuous steel sheets through the steel mill for rolling or plating or whatever you're going to do to the steel, and you bring the sheets together with a great big flash welder, and it might be 8 feet wide, and here you may need that magnetic field to move the arc back and forth like you want across that sheet. And you bring the two sheets together, you start a little arc, you pull it apart, let the arc melt the edges, keep on pushing it closer and closer, and finally when you're ready, you slam it together and make your weld. Very expensive equipment, fast, very cheap equipment, slow. Neither one of them is really a very good thing to have to do in the field because the equipment's big and heavy and bulky. This one they do in the field, this one they can do in the field, but what they like to do in the field is thermite welding, which has been around for a long time. There's a very famous practical joke, prank, vandalism, whatever you want to call it, that virtually every university in the country claims that they did it, but it actually was MIT students. I think it was back in the 1930s. The students, five or six students, went to one of the trolley cars. There used to be trolley tracks right here on Mass Ave in other parts of Boston. And I don't know exactly where they did it, but I have read in the MIT archives that it was MIT students, and they did get expelled for doing this. But a couple of them got on and kind of fumbled for their change to make the conductor keep the car stationary, and the other 4 set off thermite reactions and welded the wheels to the tracks. Okay, so a very fast process. And what happens is you take some sand molds. They probably didn't really use sand molds because they weren't trying to make a really good weld. But in the field, and I went down to Dedham, Massachusetts to see the MBTA doing this on one of the lines. You got your rail, and you put some sand molds that are designed. They're already pre-molded to the shape of the rail, and you have two clamshells, and you bring them together around the rail. It has a little funnel at the top, and you put a little piece of aluminum in here. Just aluminum, a little sheet of aluminum, very thin aluminum. And on top of that, you pour a mixture of iron oxide and aluminum. And this basically looks like sand that's going to integrate. There's actually a big bucket up here. So the thing actually, the bucket probably stands about this tall on top of the rail. And you pour this mixture, it looks like, well, it's not exactly child's play sand, but it looks like sandbox sand, but it's a little more sophisticated. It's actually rust and aluminum powder. And then you need a blasting cap or something to ignite this. And when you do, you get a chemical reaction. The iron oxide is actually probably is Fe3O4 magnetite. This is rust, hematite. There's also wustite, which is FeO, but who cares? This one was easier to balance. Fe2O3 plus 2Al goes to Al2O3 plus iron. Aluminum oxide is much more stable than iron oxide, about 3 times in terms of the energy of reaction thermodynamically. And so basically the aluminum reduces the iron oxide to form aluminum oxide and iron. Plus it gives off about 200 kilojoules per mole, which is enough to heat that iron up to 2,000 degrees centigrade. The steel only melts around 1,500 centigrade. So the iron is molten. It's got about a 500 degrees centigrade superheat. And of course, that molten iron, the thing goes off like sparklers on the 4th of July, okay? The molten iron melts right through this little aluminum because this is just a valve, just a sheet of aluminum. It keeps the sand up there when it's solid, but once the reaction goes and the iron starts forming within literally 10 seconds. This whole process is over. You got this big bucket, and the sand molds on the side, but you've got this great big bucket of what looks like a sand reaction powder, and it all melts, and then the molten steel just melts its way through the aluminum and drops down into the cavity that you left between these two steel rails. And it all solidifies. You wait 10 minutes, some guy comes along with a sledgehammer, knocks the sand off, some guy comes with a grinder, and you grind it. And then you have a guy come in with an ultrasonic tester to test and see if the joint's any good. And half the time, the joint is good. 50% of them are junk. And so you have to cut it out and put 2 more joints in, of which each one has a 50% probability of success. So you can see this is not converging quite as fast as you would like, okay? Because this is not a very controlled casting process. It is just a casting process, but it's not controlled very well. And if you have about a 50% repair rate, you find that, well, half the time you go on to the next joint. The other half the time you have to cut that section out and put another bar in, and with 2 joints on it. And now you got a 25% chance that both of those will be good, right? So, but fortunately, it doesn't get any worse than 25% each time, but it's not a great convergence. But that's thermite welding in the field. Nice and cheap, very cheap, relatively fast, not great quality. But that's the way you weld steel rail together. Now,
There was a professor in the department who was a code breaker for the CIA, and he said that they used thermite. They all had thermite charges in case they ever got attacked. They put it on top of their file cabinet and burn it down.
Oh,
He
okay.
actually speculated that's what happened in 7 World Trade Center.
Oh,
No, it's-
well. Oh, and 7, building number 7. Well, building number 7, the World Trade Center,
but that's-
actually,
it was just in between all the rest of the buildings that had fallen.
right. Chris suggests that I give you the World Trade Center talk. Do you want the World Trade Center talk sometime? Oh, you gave it to him? Okay. So he gave it to you. The real problem with Building 7, anybody know what really happened in Building 7? Building 7 was the emergency command station for the city of New York, was in that building. They had something like 2 or 3 20,000-gallon oil tanks for emergency fuel to keep the generators running so they would have power even if Consolidated Edison shut down. So what happened is the same problem as in the main 2 buildings. The fuel load was just excessive for the building. And the moral of the story is you shouldn't store 20,000 gallons tanks of diesel fuel in a skyscraper, because that much fuel, a fire started, breached those tanks, all the extra fuel got out, and eventually the fire became not too intense, but too extensive, right? Did you get into intensive quantities and extensive quantities with them? It became too extensive and heated up the building over too large an area. Not too hot. I still hear twice a week someone telling me that the steel melted in the World Trade Center. And I say, no, I'm sorry. In fact, the cab driver in Houston that night, taking me at midnight, he said, oh, well, the steel melted. I said, no, it didn't. So I gave him my card and told him to get online at Nova. And he can, anyway. Everybody thinks they know what happens, including me. Anyway. Okay, so that's steel rail. People have tried other things to improve the speed of welding rail, but not just rail, other things like pipe. This is pipe like the Alaskan pipeline, oil pipe. But they're not so concerned about pipe over land, because pipe over land is not that expensive. It's not cheap to weld it, but it's not all that expensive. And you can be welding, 100 yards away on one section. You can be preparing another section here, and you can keep on laying the pipe. The really expensive pipe laying is the pipe laying that is in the ocean. When you are basically welding on a ship, and you have to pay out this pipe. It could be 30-inch, it could be 48-inch. Typically, we don't. Sometimes 52-inch. We usually don't go much bigger than that on pipe for oil or gas. But the typical cost for the barge that is laying the pipe is $1 million a day. It's not just the barge, it's all the other supply ships. You may have 7 supply ships to keep this one barge operating, because they got to bring pipe to it, they got to bring people back and forth. There's got to be an emergency ship in case something catches fire or something, so and whatnot. There's all kinds of requirements when you're working out in the middle of the ocean. And at $1 million a day, you can start figuring that out. That's $50,000 an hour, and you would like to make welds a little faster. There's a real incentive here to make the welds faster. You don't do forge welding of those pipes. They typically do arc welding, but they've done all kinds of things to speed up the arc welding process, like use 4 arcs as they go around, try to weld 2 at a time, but then you got to have a 40-foot long ship, and it's easier to double joint the pipes anyway. The standard length of these big pipes is 40 feet, but the standard operation is you go to the shop and you put them together as 80-foot lengths. Well, now if I want to double joint or weld, make 2 welds on 80-foot lengths, I got to have a 240-foot ship. Okay, that barge is going to cost even more. So typically, you only have about 1 you can weld. There's also 2 different ways of laying. There's S-laying. If this is your ship, you can lay the pipe like this, or there's, if your ship, well, there's J, this is S-lay pipe, and there's J. And J, basically, you have the pipe vertical, and it comes down like that. You can see it makes a J as opposed to an S. Here, you obviously can only weld 1 because the pipe that you're welding is held vertically. Here, it's held horizontally, but in either case, you usually have only about 1 joint you can do at a time. And so people spend a lot of time trying to figure out faster ways. There's people have tried flash welding with great big, called homopolar generators. If you go down to the University of Texas at Austin, there's a whole center for electromechanics. There's actually a professor, Herb Woodson, who was a professor of electrical engineering here at MIT in Texas, convinced him to go down there and start the center. He had developed the homopolar generators. They have homopolar generators that are about the size of this room, and they're basically just like a great big capacitor bank. And in Texas, they built these things so they would put out 3 million amperes over about 2 or 3 seconds. And so the idea is you just put the 2 pipes together, you hit it with 3 million amps, 48-inch diameter pipe, 1 inch thick or whatever, and you hope that joint just heats up, softens, and everything within 2 or 3 seconds, and you just forge it together. So you go from a 2 or 3 minute flash weld to a 2 or 3 second homopolar pulse weld. Well, the problem is it's very difficult to get that current to go uniformly 360 degrees around that pipe. There's all kinds of electromagnetics, plus it's a ferromagnetic pipe, and that kind of creates problems with the magnetic field. So you get some big magnetic fields with 3 million amps, okay? So there's all kinds of problems. They never solved that problem. They spent a lot of money on it. So it was worth doing research, right? Because you got the money to do the research. They've tried it for welding rails together. It can be done, but again, you have problems getting uniformity across there. There are also other metallurgical reasons why you actually want to go somewhat slower to keep the steel from quenching down too fast. But in any case, this is not exactly cold welding, but it kind of follows on because it's just the forge welding where you're extruding out the contamination. Any questions on any of that stuff? To finish up some of the forge welding, and then we'll get into electronic packaging. I just kind of think it's kind of fun. We're talking about great big pipes, and then we're going to talk about microcircuits. But it's not as broad a course as the one I TA'd as my first year as a graduate student, which was a chemical metallurgy course. In the first part of the course, Professor King, who's passed away now, lectured the chemistry of blast furnaces and things like that. In the second part of the course, Professor Johnson, who's retired now too, lectured particles in a box, electrons in a box, quantum mechanics. So we had quantum chemistry to blast furnaces all in one course. It's one of the broadest courses I ever took, or TA'd. Of course, it didn't fit together, but anyway, if you're if you're trying to cold weld two things together, before I put this up, remember we got the surface roughness and we get rid of that by interfacial sliding, and I can do friction welding or ultrasonic welding or whatever. But the question becomes, what materials are most easily friction welded or cold welded, and which ones are most difficult? And this is actually not a bad lead-in to electronic packaging, because you saw before, in fact, do you have some of my overheads? Yeah. I showed you thermal compression bonding. Remember the wire bonding, the little sewing machine needle type of thing, where you push these little 25 micron wires into the surface of the semiconductor package. Let's see. This, here you go. Remember, you got the wire, and you kind of have the sonotrode, and it kind of pushes the wire into the surface, and you make a thermo compression bond. And typically, they use gold wires. The problem is, well, it's not a problem, but gold's expensive, and people would like to use something less expensive. And the question is, what would be easier, if anything, to cold bond? And I just put my other slide. This is actually probably a better one right there. If you remember, they just kind of push the thing into the surface, get the interfacial sliding sideways, and go from there. Well, the problem is not the interfacial sliding getting rid of the mountain peaks. The question is, what surface contaminants are most easily removed by surface sliding? And it turns out, back 50 years ago, some British were studying cold welding. This goes to 1954. And they have this little plot, and unfortunately it got cut off here, but it's in your notes. It says oxide to metal hardness ratio. This is, I've got two surfaces, so here's a metal, and here's the metal oxide that it forms naturally in the air, and I have another piece of the same metal, and it has its metal oxide. And as I squeeze these together or slide them with respect to each other, what's going to give me the easiest cold welding? Well, it's not too hard to understand that if this oxide hardness is much greater than this, then the oxide is going to break up and be brittle, and you'll end up with little islands, little broken islands. You can think of it as ice flows breaking off a glacier or something. And then you got the metal behind it, and hopefully these little ice flows allow the metal beneath here to extrude in between, and you get metal-metal contact, and we know if there's no air around, the metal-metal contact will form strong bonds. And that's exactly what the British did. They basically took the oxide to metal hardness ratio, and they deformed two pieces of material by different amounts. Okay, this is percent deformation, 20%, 40%, 60, up to, you can't get to 100%, but you can approach it. And they found with less than 20% deformation, indium metal was the easiest thing to cold weld. Now, indium is a very soft metal. It melts at like 156 degrees centigrade, lower than lead, lower than tin. It's nice, shiny material. It has a price about similar to silver, so it's not cheap, but it's very, very soft. I mean, I could scratch it. I could gouge it 1/16 of an inch deep with my pen here, okay? Just with my hand, okay? It's very soft metal. So the metal has a low hardness. The indium oxide turns out to be very hard. Now, anybody know where indium oxide is used nowadays? Touch screen. You go to the automatic teller and you use the touch screen. They put a little film of indium tin oxide on there, and that's the conductive thing that when you put your finger on there, you change the capacitance or the resistance, whatever it's measuring. I think it's the capacitance. But it's the indium oxide is actually a fairly hard oxide. So indium can form a cold weld with only 20% deformation, because the oxide is very hard, it breaks up and exposes the metal to the metal as these two things go together. It turns out back in the early days of transistors, when we put them None of you have probably even seen one of these things. We used to put transistors in little cans, single transistors in little cans when they replaced vacuum tubes. They have a little metal can. Well, you couldn't heat up the transistor very much, or the thing would you blow it up. And so they actually would put a little ring of indium, and they would just squeeze the can down on top of this ring of indium, and that's how they would seal the thing. And basically it was a quote-unquote solder joint, if you will, and they typically use indium for that. The next easiest material is pure aluminum. You'll see aluminum on here with only 40% deformation. Aluminum oxide is very hard. In fact, pure aluminum oxide in single crystal form we call sapphire. And if you look at the Mohs hardness scale, diamond's the hardest, and then silicon carbide, and then number 8, I think, is corundum, which is aluminum oxide, or sapphire. So aluminum oxide is extremely hard, one of the hardest natural materials, and the pure aluminum is relatively soft. You see aluminum on here twice. This is an alloyed aluminum, which is stronger. The pure aluminum is the softest. And there's a wide range here. But indium and aluminum are the only two things that are less than 60%. Tin has a high hardness oxide, and it's fairly soft. If you look at all these other things, silver, copper, and stuff, they don't work so well. In fact, copper oxide is actually pretty soft. Copper is pretty soft, but the copper oxide just kind of smears across the surface like peanut butter. So if you get your interfacial sliding, you got to get a lot of it to spread out the copper oxide. Typically, with most of the common metals, you've got to get 80–90% deformation before you start seeing bonds, cold bond strengths, interfacial sliding bond strengths that are anywhere close to the strength of the base material. So for thermocompression welds, people have used gold for years. They've also been trying to use aluminum for years. The problem with the aluminum is it's just not quite as reliable as the gold. The gold doesn't have an oxide. Gold is one of the only metals that we have that doesn't form a native oxide in the air. What's one of the others? There's about 10 metals that don't. Platinum, right? Platinum doesn't. That's why you use the catalyst in the car, because you actually have a real metal surface that will absorb the carbon monoxide. If you get two carbon monoxide molecules together at the same time, they get happy and they'll form carbon dioxide and oxygen. And that's how a catalytic converter works. But the problem is, if you just have two carbon monoxide molecules bouncing around in the air, they don't come together long enough for that chemical electron transfer to occur to decompose into carbon dioxide and oxygen. But if you bring them together on a metal surface, that holds them there long enough that the electron transfer occurs. And that's how the catalyst works. Palladium, all the platinum group metals. So there's actually about 10 metals. There's osmium, iridium, rhenium, rhodium. But some of these things are pretty rare. Iridium, we only produce about 100 ounces a year in the world. It's a byproduct of platinum. It's an impurity in platinum refining. Well, you know, if you don't produce that much platinum, it's a precious metal. And now you're talking about something that's a small fraction of platinum. So iridium, there's not a lot of iridium in the world. And every now and then someone comes up with some great new application for iridium. Now I came up with one when I was your age. I was getting married. I decided I would make my wife's engagement ring. And I was going to make it out of platinum, 20% iridium. Because if you're a metallurgist and you go and look at what's the most corrosion resistant, longest life material, platinum, 20% iridium, right? The problem at the time was that people were starting to grow artificial sapphire, which is aluminum oxide. Iridium melts at 3,000 degrees centigrade, and the crucible for growing these artificial sapphires was iridium. And so there's a big speculator's market for iridium at the time. And my problem, I called up Engelhard, the world's largest platinum metals producer, and I said I'd like to order a ½ an ounce of iridium, because, you know, these little rings don't weigh that much, right? So we needed a ½ an ounce, but it was about $400 an ounce was the price listed on the futures exchange and stuff. But the real spot price was more like $1,200 an ounce. So, but they wouldn't even sell it to me at either price, because I actually had to certify that I was going to use it for something other than just making some platinum jewelry or something. So I decided that I went down to my thesis advisor, Professor Rose, and I said, Bob, could I buy, I'll pay the account back, could I buy half an ounce of iridium using MIT, because I was working on superconductivity, niobium-3 aluminum specifically, as for my thesis, and there was a niobium-3 iridium superconductor. It superconducted about 1 degree Kelvin, but there was one, okay, it existed. So I called back Engelhard and said, well, we needed to get this half ounce of iridium powder for research in superconductivity, and they sold it to us at the $400 an ounce price. I paid back the account, and I went off and electron beam melted my wife's engagement ring. A year later, 2 representatives from Engelhard showed up in my thesis advisor's office to ask about the results of the research. So I don't remember exactly what he told them, but anyway, we did get married, and so that's kind of an interesting story. Well, my wife thinks it's interesting, about making a platinum iridium engagement ring. It's platinum 20% iridium. If you go down to a platinum foundry in the jeweler's building, they usually use platinum 10% iridium. It's not as hard, not as corrosion resistant, but it's pretty good. The other big application for iridium, and I actually, about a year later, saw 75% of the world's iridium in one file cabinet in Oak Ridge, Tennessee. And that's because if you're going on a deep space probe to Pluto, there's not enough sun, energy from the sun at Pluto to run the solar cells. And so you need some way to generate energy for this spacecraft that's going to be taking 10 years to get to Pluto and beyond. And so they use thermoelectric generators. Now, a thermoelectric generator is nothing more than a piece of plutonium that generates its own heat because it's subcritical, but it gets hot. It's big enough that it generates its own heat, and will do it for the next 24,000 years. And you put it inside an iridium sphere that won't melt till 3,000 degrees centigrade. And that heat source, you basically set that up as a little thermoelectric engine, and you have these little semiconductor pieces that if they're hot on one side and cold on the other side, and it's easy to get cold out there in Pluto. Okay, in space, it's cold on one side. So you got cold on one side, you got heat on the other side, you can generate power, what we call thermoelectric power generation. And so actually the world's largest application for iridium is to spend deep space probes for NASA. But I do have a little bit of my own, even though I had to pretend I was doing research to get it. Okay, tomorrow we will start talking about microelectronics packaging and how we put together different layers of printed circuit boards and stuff.